This conference will now be recorded.
Welcome to everyone joining us today around the world to celebrate the release of the National Water Research Institute's guidance on implementation of direct potable reuse, a guide for California water utilities. This is Kevin Hardy, Executive Director of NWRI. And before I go any further, I'm going to check in and make sure that people on the line can hear me.
Got you, Kevin.
Thank you, Andy. As many of you know, NWRI's mission is to remain the nation's collaborative resource for the advancement of water resources science, policy, and innovation. This guidance was among the very first opportunities to who was then a very new executive director at NWRI. And what resulted was an overly ambitious, under-resourced effort that intended to provide elected officials, city and county managers, utility general managers, department executives, and other water resources planners, consultants, and regulators a comprehensive and sequenced overview of best practices and the successful implementation of direct potable reuse projects. Today, we're going to hear from two of our guide's authors, Dan Garrity of the Southern Nevada Water Authority and Andy Salveson of Carollo Engineers. And we'll also hear from some of the utility leaders that helped bring my vision to life. This guidance also reflects the project team's best collective judgment at the time. Mary, please advance the slide. This effort began in 2016. It was spearheaded by Ventura Water in their early drive as they began to consider direct potable reuse in California. And as the project developed, 4 other utilities joined along the way, and we'll talk about them in a little bit, but they offered critical advice on how we could bring this document to life and how it could bring value to the broader industry. Next slide. So these 5 partners, and Mary, why don't you just go ahead and advance each of those slides. The 5 partners included the Los Angeles Department of Water and Power, the San Francisco Public Utilities Commission, the City of Santa Barbara, the Valley Water District, and Ventura Water. And I want to take this moment now to acknowledge their support, and this project wouldn't have been possible without their participation and financial support. So who is our project team? Can you just advance it one more? Good. Oh, I'm sorry, back. I'm sorry, Matt. So our project team consisted of myself, Suzanne Sharkey, the 4 authors who were Andy Salveson, Adam Olivieri, Charles Bott, and Dan Garrity, and our utility leadership team that was made up of representatives from the 5 utilities. Today, we have to speak on their case studies Gina Dorrington from Ventura Water, Manisha Kothari from the San Francisco Public Utilities Commission, Hossein Ashkortab from Valley Water, and Jesus Gonzalez from LADWP. Next slide. Using this guide. This guide, as I mentioned earlier, is to support elected officials and appointed officials, utility leadership consultants, regulators, and anybody who's really interested in DPR in California. The guide was intended to provide support to them, yes, on a technical level, but on a policy level as well. And the idea was to be used from the early stages of a project's development along the way through permitting and then through implementation and startup of a potable water reuse facility. And the idea was to have this integrated, comprehensive guidance that was more accessible for people who weren't necessarily as well versed in some of the subjects as the technical folks in this area. Next slide. Again, it's a step-by-step approach to addressing implementation challenges for DPR projects. Again, the project team that we included extensive collaboration and review with all these partners. We also had participation in our workshops from the DDW. And so as we worked together as a team, what we found is this project began to take on a little bit more than what we viewed at first. We kind of initially believed that this could be maybe a spreadsheet or something along those lines, and it's turned into a wonderful document. Let's get into it now. Next slide. So from an overview, and Mary, why don't you go ahead and advance it one more. from an overview standpoint, what we sought to do was look at, and what we defined were 13 key components that are necessary to implement potable reuse projects. These components are project definition, TMF capability, interagency agreements, outreach and education, wastewater source control, wastewater treatment, multiple treatment barriers, pathogen control and monitoring, chemical control and monitoring, operations, water quality management, emerging issues, and collaboration to spur innovation. And to talk about these elements of the program, I want to hand it over now to Andy Salveson. So Andy, why don't you take it away?
All right, great. Thanks, Kevin. So first, before I go any further, I just do want to acknowledge the bookends of this project effort. Shauna Epstein was the general manager of Ventura Water, and it was her early drive and advocacy for this effort that really allowed it to get moving. So many thanks to Shauna. She's now at Beverly Hills. And Bryn Weeks, who works with me at Corollo Engineers, she carried us across the finish line and got this document to the spot it's in now, and you'll see it when you get a copy. So thanks to both of them. This effort has taken a long time to do, but implementing a potable reuse project takes even longer, 5 to more than 10 years. And so we really want to provide an opportunity to allow utilities to see the different steps that need to be enacted for a successful potable water reuse program. Next animation, please, Mary. And one more. Great, thank you. So if you start from scratch, you run quickly into a hurdle, which is there is so much information out there discussing both indirect and direct potable reuse and aspects of programs. Next, Mary. So one more. So what we wanted to do was bring together all the wisdom in the long list of documents that are referenced here into one fairly simple effort. Next animation, Mary. Great. So of course it starts with regulations. Oh, next. And that's for groundwater recharge and reservoir augmentation, and those regulations are of course summarized. Next. But in terms of the California DPR regulations, I'm sure a number of you have seen the draft versions that are out. This document did not attempt to address those draft regulations. It is intended to be a complementary document to those regulations as they move forward and as they're adopted. Next. One more, please. Great, thank you, Mary. So let's just go through each of them briefly. Again, I want to encourage everybody to get a copy of the document, look through it at your leisure, but this just goes through the different elements in this short time today. So let's start with project definition. Next animation, Mary. So there's no one ideal DPR system. Next. There's short groundwater travel time projects. Go ahead and advance again, Mary, a couple times. There's reduced dilution and reservoir retention projects, and there's raw water augmentation and finished water augmentation. And what these projects look like aren't based upon trying to hit any one of those 4 goals or types of projects. They're based upon the needs of the project themselves, whether a utility has a groundwater basin, albeit small, or a reservoir small, or how is it best to add the purified water into the potable system. And so there won't just be 4 different options in direct potable reuse in California, there'll be much more than that. The graphics in this document, though, try to illustrate some of these. So in this example, we have the community extracting their groundwater, using it, and then reclaiming it and putting it back in the groundwater basin. But the travel time is too fast compared to California regulations. It's less than 2 months. So that's a type of direct potable reuse. Next, please, Mary. Or you may have a reservoir in your community, but it is small. The time in that reservoir or the dilution in that reservoir doesn't meet the indirect potable reuse standards in the state of California. And so again, it's just a different type of DPR. Next, please. And then we have this example where the purified water is sent into the raw water line to a water treatment plant. And through that, you've got blending of the water qualities and how that impacts your water treatment plant. What kind of credits do you get through the system? It gets a little more complex. Next animation. And then we have the finished water augmentation or treated drinking water augmentation, where the water is sent downstream of the water treatment plant, blends in with the other finished water supplies, and goes to the community. Next. So chapter 2 is on technical, managerial, and financial capacity and capability. I apologize. Next animation, please. So these projects are challenging and costly. They are an absolutely a monumental engineering effort, and those that have succeeded in them should be commended. It requires substantial capabilities as it applies to T, M, and F. Next, please. Plus, regulators are looking for not only the aspects of TMF, but a broader potable reuse mindset where a utility is able to demonstrate its commitment and ability to maintain safe, purified water production for a long period of time. Next. And one more, please. So we look at, within this document, we look at the TMF and we break it down, and technical capabilities where we're looking at treatment systems, monitoring systems, what kind of operator training programs are in place, what are the O&M plans, and what are the long-term compliance records of the agencies moving forward with the program, whether that's one agency that handles both water and wastewater or multiple agencies that handle the different aspects of water treatment. Financial capabilities clearly important, not just the ability to build the facility, but to maintain it over the long run. And then managerial capability, all about ownership, management, water rights, etc. There's a lot in there. Next, please. Interagency agreements, that is a critical aspect, again, for the utilities that have to work with partners, whether it's a wastewater partner and a water partner or some other operation. Next animation, please. One more. Thank you. And let's roll through these, Mary. So institutional agreements, integrated planning efforts, water quality requirements. Next. Operations. Keep going, there we go. And so there's a great example out there that everyone points to. And there were reasons why it was so successful, and this is documented, but it's between the Orange County Water District and the Orange County Sanitation District. Next animation. And the different things that need to be evaluated in these interagency agreements, it starts with things like source control. It's a primary example of one of the many critical issues, but there's water rights and the cost of water, and the quality. So a wastewater treatment plant needs to be supplying a certain quality of water for the downstream advanced treatment. How are the projects funded? How are the regulatory questions addressed by multiple agencies? There's grant proposals for project funding, and never to be forgotten or put last is the cooperation on public outreach and engagement, where the same goals of the project and messaging about water safety need to apply to all phases of treatment, whether you're at the wastewater plant or at the water plant or in the distribution system. Next, please. So going to that outreach and education, chapter 4 highlights some of the success stories and challenges of outreach and education, as well as helping map how to implement engagement programs. Next animation. So one of the graphics here comes from the city of San Diego, and it documents how a long-term effort is able to change public opinion based upon the facts of good water quality and the need for a project. And this may be the most challenging aspect of your program is public engagement. So the guide does spend a good amount of time looking at it. Next, please. So several Water Research Foundation and water reuse documents are available and are referenced. Some of the details are provided. For example, out in Colorado, Water Reuse Colorado developed a statewide plan for community education and outreach for direct potable reuse. And examples of the information in there is how to break down your community into the different groups and organizations that are important for the success of the project. Understand what kind of priority they are in terms of engagement, and what is their category? Are these influencers, implementers, users, regulators, etc.? Next. The document also goes into communication plans and how to properly engage from that standpoint. So what is the schedule and duration of your project? What are the core goals of the project? And what is the purpose of your communication? What messages are shared with the community? Work through things like terminology so you don't confuse things, and essentially state the value of the project and how it's evenly applied to your community. Next, please. Now it starts with wastewater source control, and you're going to hear Dan Garrity in a moment talk about other aspects of treatment. But starting with the raw wastewater, source control is awfully important for indirect potable reuse projects. Next animation, please. Enhanced source control programs are the norm. Those take the national pretreatment program or the local limits work that is done by large wastewater plants over 5 MGD and expands them into this enhanced source control program. Through that, you take a harder look at the chemicals that are in your collection system that are discharged by industry. You have greater outreach programs, greater sampling programs, and in general, a much larger effort. Next animation, please. But DPR programs will require a much higher level of source control. Next. And that is for any size system, big or small. Next. And we have to just recognize as a group that the National Pretreatment Program really is a starting point for these kind of efforts. And there's a lot to come after that. Next. One more animation, please. So a primary question is, who comes first, business or water? And the answer is, well, of course, there's a water first mentality, but business can't be sidelined. It's an important part of our community, and it's really unavoidable in our sewer sheds. So an effective source control program should strive to avoid negatively affecting industries while aggressively engaging them to fully understand the waste streams they discharge and how those streams can be best handled while reliably producing purified recycled water. Next. One more. So within this document, we do talk about the conventional enhanced source control programs where extensive sampling is done within the wastewater plant, the pure water facility, and into the collection system. And a number of the facilities that do potable reuse, I've seen firsthand them be able to track pollutants from the wastewater plant back to the source in under a day. So there's really good programs out there. We're now saying what comes next after that. Animation, please. Go ahead, Mary. There we go. So a couple more. Real-time monitoring is already here. And the latest work is examining how to best implement real-time monitoring within the collection system so that we can reduce some of the sampling burden and even more quickly find the source of industrial discharge problems that are posing a potential problem for potable reuse. And with that, I'm going to hand it over to Dan Garrity.
All right, thank you, Andy. So one part of potable reuse that's often overlooked is the front end of wastewater treatment. And wastewater treatment in general is important because it sets the foundation for what's happening later on. And so next animation, please. The part that I wanted to focus on is the importance of setting that foundation. So a consistent water quality in terms of a few examples here, total suspended solids and turbidity, total organic carbon and nutrients, that's going to make that advanced treatment train work a lot better. So some particular examples, if you have variable total organic carbon, for example, and you have an ozone process, that's going to create a dosing problem because variable total organic carbon is going to cause that ozone dose to vary over time. Another example with nutrients would be nitrite. And so if there's variable nitrification or incomplete nitrification, then that's going to impact the level of ozone dosing that's needed in that type of system. Another example that relates to what I've done in the past in terms of research is looking at the importance of biological treatment on trace organics. And so often full nitrification is important for getting reductions in a wide variety of trace organics, which reduces the load on the advanced treatment train later on. Another issue has been return streams. And so return streams have been identified as a potential source of NDMA precursors, for example. So by limiting those return streams, it's going to possibly solve problems that might pop up later on. Next slide, please. And so a project that actually Carollo is leading right now is actually looking at this very question. So how does upstream wastewater treatment impact downstream advanced water treatment? So in terms of ozone performance, membrane performance, there's a lot of implications for whether it's just BOD removal or if you're getting full nitrification, there's going to be implications further downstream. Another thing that I wanted to point out is where the water is pulled from in order to feed an advanced treatment train. And that's something that came up in a project that was led by Trussell Technologies in the past, where they were looking at parallel pilot scale treatment trains, one ozone biofiltration based and one membrane based. And the feed water, there was the potential to take secondary effluent or tertiary effluent. And so the tertiary effluent might be more consistent, might be slightly better quality, but that tertiary effluent was chloraminated. And so that would lead to NDMA formation going into the front end of the advanced water treatment train. So these are the types of issues that need to be balanced when you're piecing together the overall treatment train for a potable reuse system. Okay, next slide. And so that brings us to the multiple treatment barrier, multi-barrier approach. And so the part that I really wanted to highlight here is this concept of the 4 R's. And so that's reliability through redundancy, robustness, and resiliency. And so when you look at the figure there on the left, when we talk about redundancy, you're thinking about multiple treatment processes in series that are dealing with a certain contaminant or groups of contaminants. And so when we look at robustness, now we're looking vertically. And so we're looking at a treatment process that's able to simultaneously handle a wide range of contaminants. And then in terms of resiliency, we want that treatment train or a treatment process in particular to be able to handle those short-term upsets that might happen. So how resilient is that system to an operational upset? So when you look at the draft DPR regulations or even the existing groundwater reuse regulations or surface water augmentation regulations, a lot of these concepts are built in, and I'm providing a few examples here from the draft DPR regulations. So by requiring more than 4 processes per pathogen or more than 3 treatment mechanisms per target, that's building redundancy into that system to make sure that we don't have a failure that might have an implication for public health. Okay, next slide. And so in order to determine what level of redundancy that we need for a system, one way of doing that is doing what's called a quantitative microbial risk assessment. And so a few different examples of the types of questions that you can answer with a QMRA that are listed there on the left. What I wanted to point out is that, and we'll talk about this a little bit later as well, is that there's a series of research projects that are ongoing or recently completed that deal with a lot of the remaining questions related to direct potable reuse. And so one is this DPR1 project where we developed a quantitative microbial risk assessment tool. It's really user-friendly, gives people the opportunity to run a number of scenarios very quickly to answer these types of questions. So for example, what magnitude, duration, and frequency of failure can be tolerated before a risk benchmark is exceeded? And I'm providing an example there. And so that gives us an idea of what level of redundancy do we need to make sure that we're adequately protecting public health in a potable reuse system. Okay, next slide. Which brings us to pathogen control and monitoring. And so particularly with potable reuse, where we have these really high quality drinking waters on the back end, this brings up the somewhat of a problem because we're unable to detect any type of pathogens at these very, very low levels. And so instead, what we have to do is take this risk assessment approach, and we have to look at what's going into a treatment plant, what's coming out at the tail end that we're trying to target in terms of protecting public health. And that difference is going to give us an idea of what level of treatment that we need in between to make sure we're hitting that target on the tail end. And so I mentioned that DPR1 project in the middle that's shown there. That's the QMRA tool. There's also a DPR2 project that's improving characterization of raw sewage pathogen concentrations. So by better characterizing what's coming in on the front end of a treatment plant, what levels or what targets we're trying to reach to ensure that we're protecting public health, that's going to give us the LRV target that we need to achieve that. Okay, next slide. And so there's a number of examples that are shown in this document in terms of what are the typical credits for a unit process. So there's a few examples here. I'll focus on reverse osmosis for a second here. So depending on the surrogate that is used to verify the performance of the RO system, that's going to give you an idea of what type of credit you might be getting in a potable reuse system. So often these regulatory LRVs are conservative, again, to ensure adequate public health protection. But there is potential, and this is highlighted throughout the document, to seek higher credits for a particular process, as long as those credits can be demonstrated and also verified with a reliable surrogate monitoring framework. And I'll talk about that in a little bit later. Next slide. And one more. So when we're building in this redundancy, there's, again, a balance. So balance is one of the common themes throughout this document, is that you don't necessarily want to keep adding on treatment processes if it's not warranted. And so there's a need to balance redundancy, or this LRV cushion, with the added operational complexity and costs associated with that. So just adding another process, you might think that that's going to provide a benefit in terms of water quality and public health protection, but there's the potential to actually have a negative impact because of the added complexity of that process. So that's something that has to be considered in the design of these systems. Next slide. And so, oh, sorry, well, you can go back one. And so with that last bullet there, public health protection involves a combination of treatment. So that, again, that's the possibility of adding another treatment process, but maybe instead of adding another process, we can make sure or have better verification of the existing processes with better monitoring, or having more response retention time. So balancing those three different components, again, is another way of achieving our goals without just simply adding additional treatment processes. Next slide. And so, like I mentioned earlier, ensuring that these processes are working correctly and getting these regulatory credits, these LRV credits, one of the ways of doing that is identifying these critical control points. Next animation. And so identifying a critical control point is important for both chemical and microbial hazards. And so these critical control points are often going to be linked to, in the easiest sense, looking at microbes. If you're trying to get an LRV credit for a certain pathogen, it's often going to be demonstrated at a critical control point. Next animation. And so at each of these critical control points where we want to demonstrate an LRV, there's often going to be a surrogate associated with that. And so identifying an appropriate surrogate for verifying process performance through monitoring is going to be an important component of achieving that LRV credit. Next animation. And then once we have that critical control point and the surrogate, we can establish limits or windows on the performance of that process and that surrogate. Next animation. And so that once we possibly go outside that window, then that's indicating that there's some type of failure associated with that process. And so one of the important things is to have a plan on how to address if that failure occurs. Next. And so this is showing a potential treatment train for a potable reuse system. And so the numbers there at the top represent potential critical control points. And then for each of those critical control points at the bottom, there's a potential surrogate that we can use to make sure that that process is operating the way that it's intended. Next animation. And then one more. And so what I want to point out here is that one size does not fit all. And so for RO in particular, that's what's highlighted here. These are potential surrogates that are either being implemented already or tested to see how well they work. And so for one system, electrical conductivity, which provides a slightly lower LRV credit, might be suitable, but then for another system, they might want to seek, again, more credits for this RO process. So there might be an opportunity to demonstrate the use of TOC, fluorescent, sulfate, or one of the more recent ones being strontium, in order to get more credits for a particular process. So again, not necessary for all, but that opportunity does exist. Next slide. And so last one that I'm going to talk about is chemical control and monitoring. And so very similar to what we have with the microbial side, just different groups of targets that we're looking at. Next animation. And then one more, I'll put them both up there. So with chemicals, when you look at, and I'll talk about trace organics here. So trace organic compounds are present in wastewater, obviously. And so one thing that we've learned over time is that the typical concentrations of the vast majority of trace organic compounds, even in a secondary effluent, are going to be below some public health benchmark or even maximum contaminant levels. But that doesn't necessarily mean that that's good enough. And so there's a number of reasons for that. So there's one reason being that there are unknowns out there. And so by having this robust multi-barrier treatment, we're able to potentially address those unknowns because we have a high level of treatment targeting things that we already know about. And then the other thing that comes up is public perception. And so just in general, people do not necessarily want to have trace organic compounds in the water that they're drinking. And so whether or not it poses a public health risk, there's going to be the public perception question that also needs to be addressed with the potable reuse treatment train. Next slide. And so here throughout this document, there's examples of compounds that many of you are already familiar with. So for example, nitrosamines, sucralose. What are the public health benchmarks associated with those? What are the treatment performance benchmarks associated with those? This document will highlight some of those more common compounds that'll become a frequently discussed target of a potable reuse treatment scheme. Next animation. And so a well-designed potable reuse system is not only going to address the chronic exposures, but also acute risks. So depending on the compound that we're talking about, some are going to be more chronic in nature. So for example, NDMA with a cancer endpoint on the public health significance of that compound is going to be more chronic in nature, but there are going to be compounds, for example, nitrate being a more common one, that poses an acute risk. And so a potable reuse treatment train should address both the chronic and acute risks associated with chemicals. Okay. Yep, okay. And then the last thing that I'll talk about is the importance not only of RO-based treatment in California, but outside of California, there's opportunities for potable reuse systems to rely on ozone biofiltration. And so Crollo Engineers was a leader on the ozone biofiltration front in demonstrating that that does provide a robust alternative to membrane-based treatment for things like contaminants of emerging concern and trace organic compounds. You get one more animation. And so this is just highlighting the number of compounds that are detected in a secondary effluent. Again, the vast majority of those, even in secondary effluent, do not pose a public health concern at the levels that they're detected, but with advanced treatment, we're able to eliminate the vast majority of those. And then the ones that are detected in the end are going to be present at very, very low concentrations with de minimis risks. And so even though ozone biofiltration is more common in potable reuse systems outside of California, with the new DPR regulations, it's possible or probable that you're going to see more ozone biofiltration that gets incorporated into these treatment trains. And again, that provides a very robust barrier against a wide variety of compounds. And so it's going to reduce the load and the burden on downstream processes like RO, where most of these compounds are typically concentrated and then have to be dealt with the concentrator brine. Okay. And now I'll pass it back to Andy.
All right, great. So if you followed all these processes and you've enacted your program and you've got a pure water facility being constructed or ready to go, you still need operators. And we face a challenge in this industry with sufficient operators for our water and wastewater plants. And as we move to more and more potable water reuse, we need these advanced water treatment operators. And I'll point out that there's a lot of growth in the potable water reuse industry, and so these operators are going to be at a premium. Several years back, next animation please, the industry, whether it was the Water Research Foundation or Cal Nevada AWWA with CWEA, said we have a shortage on operators. We need a training program and we need a certification program. And what we saw was several things come forward. So the table on the left points some of these out. The job requirements were developed through a job analysis report by Cal Nevada AWWA and CWEA. Training materials on the different types of advanced treatment was developed by the Water Research Foundation, led up by Troy Walker, a project that that I participated in with him and his team. And then the test exams were actually developed. Grades 3 through 5 AWTO exams have been completed, and these are now being administered. As a matter of fact, I believe last time I checked, there were 3 AWTO 5 certified folks now, but there's a lot more grade 3 and some grade 4. So there's a lot of movement, but there's need for more. Next animation, please. And I want to point out that this AWTO, it's focused on potable water reuse, but it can also apply to a lot of other types of advanced treatment of water. Next slide, please. Okay, so stepping back just a bit though, it's important from the operator standpoint to understand that potable reuse is the intersection of wastewater and drinking water treatment. And both those mindsets are valuable, but they need to overlap. So the wastewater operator is absolutely critical to have a good understanding of the impacts of wastewater effluent on downstream advanced treatment. And the water operator needs to understand the goals of public health protection, and bringing them together is the AWTO. Next. So the who qualifies for the AWTO test? Well, all you have to do is have a California or Nevada wastewater or water operator in the grade 3 or higher range. You can then take the similar grade 3, 4, or 5. You got to start at grade 3 and move your way up. AWTO exam and get your approvals. Next. So now you've made the water, you're operated the facility, but you've got water quality management. And so you see we're kind of following the drop of water through the system in this guide. Next animation, please. And so when you're introducing a new potable reuse supply, you've got to take a close look on the impact on delivered water quality, distribution system stability, and blending location, whether it's ahead of the wastewater or ahead of the water treatment plant, within the water treatment plant, or in the finished water. Next animation, please. And one more. So the guide goes through and follows some of the industry's best practices and walks us through 5 steps to understanding and implementing a stabilization process, starting with data review, working through desktop evaluations and stabilization alternatives. And then we recommend coupon testing and pipe loop testing, actually demonstrating in the stabilization in a distribution system. And then that leads to the implementation of the optimal solution. Next, please. And one more. So on emerging issues, this industry's done a great job to stay out in front of most challenges. But we do need to recognize that things come up, and sometimes we need to adjust. So early in my career, there was the rise of NDMA in the late 90s, and the development of UV for photolysis, whether medium pressure or low pressure, and that was well addressed through treatment. Then came 1,4-dioxane. We saw the development of advanced oxidation for UV AOP processes in particular, and that also provided a broader barrier for chemical pollutants that could be in RO permeate. We also saw the rise of concern about hormones, pharmaceuticals, and personal care products. What we found through the research that was done was several things. First of all, we're really good at removing those. And second is that they're a broader public perception challenge than they are a public health challenge. PFAS is now on everybody's mind, and it should be. PFAS represents risk at nanogram per liter levels. And we currently have only a few tools to remove PFAS from the water stream. And then you say, well, what's the latest today? There's always something new. Of course, we are dealing with viruses, emerging pathogens, listed a few here. But what we know based upon the research is that these advanced treatment trains do provide robust removal of all pathogens, including the emerging ones that the public is potentially focused on. Next slide. Next animation, please. And Kevin, I'm going to turn it back to you. Aging Kevin Hardy.
Yeah, and I'm sorry I took a little longer, but yeah, no. So let's move to the next. Let's move to the next animation, Gina or Mary, sorry. So what we know, I think, looking back historically, and also just from our own professional judgment, as we know that this overlap that Andy talked about has been acknowledged by DDW. And you heard them say a few weeks ago when they released in their public meeting their DPR early draft, that this joining of the two meant that the DDW was really interested in understanding water quality and understanding, they use the words known for sure, and the ability to respond to failure to divert off-spec water. And these are both things that are incredibly important. And so to do that, these 5 research projects were identified. Dan talked about research projects 1 and 2. DPR, I should say the DPR 1 and 2 are both, Brian Pexon is the PI on those work, and that work's done. It's helping with the regulations now. DPR 3 was a wastewater-based epidemiology study that sought to determine the feasibility of measuring pathogen concentrations during community outbreak events. They wanted to further investigate issues that are critical to characterizing the highest level of pathogens expected in untreated wastewater. So the effort involves literature review and some sewage monitoring studies, as you might expect, and that, of course, turned out to be relatively timely. DPR 4, which is being carried forward by, as the PI on that was Jean-Francois Dubourreau. This is another case where we're identifying treatment processes that can provide some averaging with respect to potential chemical peaks, particularly for chemicals that have that potential to persist through advanced water treatment for DPR. And I think the idea is that averaging can take the form of a treatment process that causes removal or transformation of the contaminant, or it can be a blending or dilution scheme to reduce chemical peaks to background levels. And DPR 5 is the non-targeted analysis for unknowns. That's being done by SQURP and is looking at kind of the state of the art on the analytical methods for trace organic compounds, as we talked about a little bit earlier in the presentation. In addition, NWRI was able to present a 6th element of research, which was an internal source control independent advisory panel. That work also was received by DDW and considered in the development of their early draft regulations. And as we look forward, I think what you're going to see is we'll see more work on bioassays that we had to come up with guidance for a few years ago when they first were approved and mandated rather by the water recycling policy. I think we're going to see additional tools in this space on rapid response. And I think that's natural, considering that we're going to be engaging new partners on public health and out in the business community as we're doing source control and public outreach. So next slide. So next, I want to take this opportunity to give 4 of the utility leaders who participated in this effort an opportunity to talk about the things in their DPR journey that they've learned from it, and the case studies specifically that they included in the report. And what we wanted to do is give them an opportunity to talk about both. Obviously, the case study that we included in the report has got some limitations, and this space is moving so fast that we wanted to let everybody know the most up-to-date information possible. So if we can go to the next slide. I'd like to take just a moment, bring Gina Dorrington in and have Gina present the Ventura water case study. Gina?
Thank you, Kevin. Hi, I'm Gina Dorrington. I am the Assistant General Manager of Operations for Ventura Water in Ventura, California. And here in Ventura, we faced a myriad of challenges to our water portfolio. One being a consent decree on our wastewater effluent discharge, mandating us to remove that discharge from the Santa Clara River estuary, which was a federally endangered species listed habitat, by the year 2025, and at least 50% of that water needed to go to a beneficial water reclamation use. On our water supply side, Ventura is solely reliant on local water supply with the Ventura River, our groundwater basins, and Lake Casitas. And we faced several legal and environmental challenges on the Ventura River, restricting our use. And then the formation of SGMA and the groundwater sustainability agencies on our groundwater basins started to bring along a restriction in our allocation for pumping of that groundwater. And through the last period of drought, we saw our Lake Casitas go down to below 40% capacity. So we started to see a gap between water supply and demand starting to hit us around the year 2023. So potable reuse became an optimal option to get us to where we needed to be and enhance our portfolio, as well as address some concerns we had with meeting secondary standards on TDS and sulfate in our groundwater supplies, and providing us with a consistent, reliable source that could get us through the next future drought periods. The DPR was our original plan to go through, because we didn't have a large reservoir to augment, or we didn't have a sole groundwater basin to inject into. So we would be investing a lot of money in infrastructure to treat our discharge to drinking water standards, injecting it into a groundwater basin where other agencies could reap the benefits of that without paying for the infrastructure costs. So we wanted to try to ensure that water supply was secured for Ventura. And with the management of the GSAs, we weren't sure if we would even have the ability to inject and whether our allocation to pump back would be equal. So DPR was offering us some flexibility in that area, and it was also looking a little more economically feasible based on the additional well fill infrastructure we'd need with IPR. So we built a demonstration facility, and it was very successful. We had outreach efforts to over 600 children and residents within Ventura, and polling results showed a very wide, almost 2/3% acceptance of direct potable reuse. But when it came time to start embarking on our environmental impact reports and bringing in preliminary design of the project, our regulations were still not in place for direct potable reuse. And without that comfort, knowing that we could get a DPR project permitted by the time we needed to have this diversion in 2025, our city council went ahead and decided to plan for an IPR project. So during this process with the NWRI and joining with the other agencies we have here today to try to get those regulations moved forward for DPR, we had to move forward cautiously as we started planning for this project. And so today we have an IPR project with some flexibility to go DPR if those regulations come through, and they provide us with still an economical way to go to direct potable reuse. Thank you.
Thank you, Gina. That was informative. And it's always good to hear about the journey that different utilities are on. Let's advance the slide, and we'll hear about the journey that, who are we on next? What's the next slide, please? Next slide is Hossein Ashkotab and Valley Water.
Hi, Kevin. I hope you can listen to me. Is it okay?
Yes, we can hear you.
Okay. Thank you very much. Everybody, good afternoon. This is Hossein Ashkotab. I'm the manager for recycling and purified water at Valley Water. Really pleased to see this study coming to the end. We have been part of it. It's really exciting at the same time that the DPR regulation is moving forward. And I want to start with the goal that the Valley Water Board came up with is that 10% of total water use should come from the recycled water. This could be both non-potable and also potable. Then another thing is that really in the last 3 years, we have worked on the countywide water use master plan, so we call it core plan, which is the basis for expansion of recycled water in our county. Core plan has identified a preferred mix of non-potable and potable reuse with 6 different alternatives, which is achieving up to 24,000 acre-feet per year for potable reuse. This includes IPR and DPR, which is both IPR in groundwater recharge and DPR both in raw water and augmentation and treated water augmentation. In September of last year, Valley Water Board approved a design, build, finance, operate maintenance called DBFOM to implement the first potable reuse of 11,000 acre-feet per year of purified water for groundwater recharge, which is going to be purified water from the wherever wastewater treatment plant is, put the advanced treatment in there, and then going from there, either from San Jose side or from Palo Alto side, going to the Los Gatos treatment, Los Gatos pond system for groundwater recharge. And we should begin the operation in 2028. So it's not that much time. So we are really into hurry up and start working on the design and also hiring and going through the P3, which is part of the process that the board has agreed on to going to do under the public-private partnership. So this project is not only is going to be exciting for us because of it's going to have a groundwater recharge, also in the future, based on the core plan, it has been going to be expanded up to 24,000. So 11,000, around 11,000 acre-feet per year is coming from groundwater recharge, and the future is going to be additional up to 24,000, which we call it flexible, under the core plan is going to be covered by raw water augmentation and or the treated water augmentation. So it is, it's going to be a lot of challenges here, but actually based on the, so far the core plan that we have, it's been very important to look at all the options that we have and then see which one is going to be in the future is going to help us from 11,000 move to 24,000 acre-feet per year, which this recent regulation activities that happening and the amendment is going to help us to see better looking into the future for DPR. At this time, I would like to stop here and give it back to you, Kevin. Thank you.
Thanks, Hossein. And you can begin to see, everyone, the diversity of the sorts of challenges that utilities face in these DPR projects. Just the planning and integration of ideas among the various different sorts of agencies that are involved in these kind of projects. Let's advance the slide. And let's also look at a different kind of challenge where that SFPUC faces. And for that, we'll bring on Manisha Kothari. Manisha, take it away.
Thanks, Kevin. Hi, everyone. Good afternoon. My name is Manisha Kothari, and I am with the San Francisco Public Utilities Commission. I manage our alternative water supply program, which includes potable reuse. So for San Francisco PUC, we serve about 2.7 million customers across 4 counties here in Northern California. And you know, a number of our customers are wholesale customers outside of San Francisco that we serve, 27 wholesale customers. And we also serve the city and county of San Francisco, and that is what we call a retail customer of ours. So I'm going to focus this discussion, our case study here is really focused on San Francisco and the city and county of San Francisco and some of the unique challenges we have in the city. In San Francisco, there's no real potential for indirect potable reuse. We don't have any kind of environmental buffer, and we don't have a water treatment plant within the city limits. Our water actually comes into San Francisco through our regional water system outside, and so it is it basically gets treated before it gets into the city limits. So IPR is out for San Francisco. So that really limits us to looking at treated water augmentation in the city. Within our regional service area, we are looking at all forms of potable reuse, but within San Francisco, we are really focusing on treated water augmentation and what the potential is there for treated water augmentation. We did a research project that lasted about 2 years, a little over 2 years, that we wrapped up last year, was funded by the Water Research Foundation. It was also had some separate grant funding from the Bureau of Reclamation. And this research project was really intended to look at doing a very small project within our headquarters building in San Francisco, taking the wastewater that is generated in that building, treating a stream of that wastewater, and basically testing all steps of the treatment processes to be able to determine what kind of water quality we're getting. We also did some bioassays. As part of that research project, we also exposed our treatment operators to the treatment processes to have them basically learn how the treatment processes work. Now, these are wastewater treatment operators who were familiar with treating wastewater for non-potable purposes, but not with the potable side. So learning the reverse osmosis processes and some of the sensitivities on the water treatment front. That was an important goal of the project. We also did some public outreach and focused a lot actually on in-reach, if you will, but in getting staff who work in the building and throughout the San Francisco PUC to visit and become familiar with the technology and what we're looking at. We encouraged people to ask a lot of questions, since we are at the very early stages of research and thinking about potable reuse in San Francisco. So I think that was a very successful research project that we wound up, and it's basically leading to the next step now, which is exploring the potential for treated water augmentation in San Francisco by looking at the different facilities that we have, the resources, the reservoirs we have, the plumbing that's in place, and sort of the distribution networks and how we can develop project to really look at the maximum potential for potable reuse through treated water augmentation in San Francisco. So you know, it's a step-by-step process. Certainly for us, we're very pleased to be part of developing this guide and in looking at the DPR framework that's coming out now. And so we're very excited about the collaborative effort. Thank you very much. I'm going to turn it back to Kevin.
Thank you, Manisha. And if we can advance the slide then, one more. We're going to conclude today's program with the case study from the Los Angeles Department of Water and Power, who has, in their own twist of scenarios, has engaged in Operation Next. And today we have with us Jesus Gonzalez from LADWP. Jesus, take it away.
Thanks, Kevin. I'll continue to give you a hard time, and I presume you wanted to save the best for last. But all kidding aside, thank you again for allowing DWP to be part of this distinguished panel. In the interest of time, I see that we have about 15 minutes left. I'll be brief, but I did want to provide some perspective as to how DPR fits into LA's water future. As some of you know, LA made national news 2 weeks ago regarding our plans to maximize recycled water to address the need for a resilient and local water supply. In those national stories, Mayor Garcetti discussed LA's plan to recycle 100% of the city's water supply by 2035. We refer to this ambitious effort, Kevin, as you mentioned, as our Operation Next program, a multi-billion-dollar effort that once completed will account for 1/3 of the city's water supply for the 4 million customers we serve. So again, a very, very big deal for those of us here in LA and the customers we serve. So recognizing that Operation Next is a hybrid project, as we call it, a combination of IPR and DPR. We're also concurrently developing a DPR demonstration facility at our Headworks Reservoir Complex. The objective of this demo is to analyze various advanced treatment strategies, alternative purification processes, blending strategies, and a whole host of other approaches. But our intent with the demo is to share this research with the entire industry, and specifically share it with agencies that are also considering DPR as a potential option for them. So Kevin, back to your original question, LA is very much planning to implement DPR as a potable reuse strategy, and given the large role that it will play for our future plans here in LA, we're very much engaged with the research. So again, thank you, and on behalf of all of us at DWP, thank you for your work on the development of this guide. So Kevin, thanks again. Andy, same to you as well. I'll turn it back to you, Kevin.
I appreciate that, Jesus. Thank you. And let's advance the slide. And now it's a time, I think at this point, you know, that you've seen very much of the guidance document. And what we would like and what we're asking you to do is if you would be so kind as to email Mary Collins at the email address on your screen now. She will provide a complimentary electronic version of the guidance. Those will be available for you here in the next couple of days, but we need your email address to get it out to you. So we look forward to hearing from you on the documents. I also wanted to remind you that comments on the early draft are due back to the State Water Board on June 25th. And I also want to remind you that the NWRI fellowship applications are being accepted through the end of May. And if you know anybody who would benefit through those fellowships, and we've had hundreds of fellowship recipients through the many years of NWRI's existence that have come back to make significant contributions in our space. I would encourage you to have them contact Natalie to apply, and we'll look forward to evaluating their qualifications. I want to take a moment too to thank each of our presenters today. Each one of you stood up really above and beyond the call of duty, so thank you. All the authors and utility leaders and the folks who presented and prepared and participated in the workshops that we had to develop this. I want to thank you for your efforts. This has been a long time in our effort, but again, a labor of love, and I thank each of you. I want to thank everybody who showed up today, and I think our attendance was excellent. Thank each of you for tuning into this webinar, and more importantly, I want to thank you all for supporting NWRI. I wish everyone to have a great rest of your day, and we look forward to working with you all on this important project in the very near future. Take care and goodbye.